Okay, absolute value here today. This is Mr. Gieske. Absolute value is another one of those topics I think that a lot of kids can do, but they don't really think about. And I put myself in that category. I didn't really think about absolute value very carefully until I was studying physics or doing some complicated problems in college. So I just want to start with the definition. The absolute value of a quantity is its distance from the origin. Distances are always positive, so an absolute value is always a positive quantity. Uh, The thing I like and dislike about this definition of absolute value is that it's given in a graphical format. So it's hard to think about distance from the origin when you don't have a graph in front of you. So, problems that we'll get to, like the absolute value of x plus 3 is less than 4, can be done analytically, but I don't think you really want to do it analytically, just pushing some symbols around until you think about the graphical impression, because frankly the definition is graphical. So I just want to go through a couple of things simply and then grow more complicated. So what does the absolute value of 31 really mean? I mean, I think everybody who's watching this knows that that's just equal to 31, but if you look at the graph, this is the origin and this is the point whose coordinate is 31, and you're asked how far is the point that has the coordinate 31 from 0? Well, that distance is 31. Likewise, if I asked you what's the absolute value of negative 16.3, you'd say, oh, that's 16.3. But you need to be thinking about, oh, by the way, this is a number line, so it goes on forever. You need to be thinking about the fact that if you were to mark 0 over here, and if you were to mark negative 16.3, this point, whose coordinate is negative 16.3, and you ask yourself, how far away is negative 16.3 from 0? You'd be like, oh, duh, that's 16.3 units. Okay, so I think that's pretty straightforward. What if we, just to throw a monkey in the wrench here, what if we try to do this in two dimensions? So if I did a coordinate plane and I asked you for the absolute value of the point 10, 7, you'd be like, wait a minute, you can take the absolute value of a point? And I say, sure. If the absolute value is simply the distance from the origin, you'd say, okay, fine. Let's call that distance d, and I just need to figure out what d is. And you might go about something like this. So what I'm doing right now is the absolute value of 10, 7. That looks goofy, I'm sure, but so what? You might drop a vertical here, a perpendicular, and you'd call this 7, and you call this 10, and you'd be like, oh, I can just do the Pythagorean theorem for this particular absolute value problem. In fact, you'll recognize that you can use the Pythagorean theorem for every two-dimensional absolute value problem. So you would say that the absolute value of 10, 7, well, you might do something on the side here. You might say 7 squared is equal to, 7 squared plus 10 squared is equal to d squared. And what we want is d. Okay, so you might say that the absolute value of 10, 7 is equal to the square root of 7 squared plus 10 squared, which we all know to be the square root of 149. And while we're here, why don't we estimate the square root of 149? Well, 12 squared is 144, and 13 squared is 169. So that means that the square root of 149 has to be between 12 and 13, and a little closer to 12. That's just for fun. Okay, so I hope that example is an unfamiliar context, but sometimes taking things out of context and trying them in a new place really helps you learn the way to do them in the context that you're used to. One more little example out of context, and we'll try it. What do you think this means? So the absolute value of some points x, y equals 3. The absolute value of a point equals 3. So What we're trying to say is what must be true about x and y if the point whose coordinates are x comma y always has absolute value 3. Well, if you understand the definition of absolute value, you would say the set of points x comma y that is always, set of points that are equidistant from the origin. And not just equidistant, but always, you could say, that are all, that are all 3 units from the origin. So if we have a set of points x comma y that are equidistant from the origin, or all 3 units from the origin, what have I just described? Well, here is a graph. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I know these 4 points are all 3 units from the origin. What kind of shape would you say is described by being a set of points equidistant from another point? Well, that's going to be a circle. So I'm just trying to help you understand the definition of the absolute value. So this is called a locus of points. A circle is a locus of points equidistant from another point, and this one in particular would be described by the absolute value of all the points x comma y that lie on this circle would be described by that equation. Okay, so that's enough of the unfamiliar stuff. I hope you understand what the definition of absolute value really means. Let's just try some familiar exercises, and we'll apply our understanding. The instructions for all of these are solve for x. That means find all values of x that might make this, that will make the statements below true. So if the absolute value of x is equal to 6, list all points x whose coordinates are, all points x who are 6 units away from the origin. Now this is a one-dimensional problem because there's only one variable. Okay, so here's the origin, 0. Give me all the points that are 6 units from 0. Well, there's 6, and then there's -6. So you would say, you have to be careful with my language here, but it really is x equals 6 or x equals -6. And the graph of that would be like this. Or because x can't be equal to 6 and -6 simultaneously, so you're really saying that there are 2 solutions. And sometimes you see people list them as a set. In fact, if they did list it that way, they would list it from least to greatest. And that would be the set of solutions. How about this one? The set x plus 3, the absolute value of x plus 3 equals -2. How does this work? Well, you should ask yourself to look at this as the absolute value of some unknown quantity has to equal -2. The absolute value of some unknown quantity has to equal -2. How can an absolute value equal a negative number? Well, it can't, so there are no solutions. The absolute value of x plus 3 can never equal -2 because the absolute value of a number or a quantity is always positive. Okay, how about the absolute value of x plus 3 equals 4? Okay, that's a legal request. There are numbers x that will solve this equation. So I guess to think about here is to say to yourself, well, I have the absolute value of some unknown quantity, and it's equal to 4. What must that quantity be equal to in order to have an absolute value of 4? Well, that quantity, x plus 3, must equal 4, or x plus 3 must equal -4. And then you solve for x as you would. X plus 3 equals 1, x equals 1 or x equals negative 7. And then you can test. You can go back here and say x equals 1. You put it in here. 1 plus 3 is 4. The absolute value of 4 is 4. Negative 7 plus 3 is negative 4. And the absolute value of that is 4. So you're just applying the reasoning that we put up here on this x, the absolute value of x equaling 6, saying x equals 6 or x equals negative 6. But instead of your unknown quantity being x, your unknown quantity here is just x plus 3, because that's what's inside the absolute value bars. So the unknown quantity has to equal 4, or the unknown quantity has to equal negative 4. And just because your unknown quantity is complicated doesn't matter. Just go about solving your two equations independently. And then when you're done, you would collect them into a set. That represents a solution set. Both of the collection of numbers there solve the equation over here. Okay, and then we get into pretty common problems that you see. These are a little harder. What about the absolute value of x plus 3 being greater than 4? Okay. So I go back to my number line, and I think about the origin being here, and I think about this being 4 units away to the positive side, and this being 4 units away to the negative side. And if the absolute value of this quantity x plus 3 is going to be bigger than 4, then it must occupy these portions. X plus 3 can be anything inside of the blue areas. Okay? So what have I just described graphically? Well, this one over here is the set x plus 3 is greater than 4. And this set over here is x plus 3 less than negative 4. Okay? So in order for an unknown quantity to have absolute value greater than 4, that unknown quantity must be itself bigger than 4, or the unknown quantity must be less than negative 4. So there's an or in here. Okay? So that's important that this is an or. We're not trying to satisfy both of these things at the same time. The unknown quantity can be in this region, or it can be in this region. So if you solve these equations independently, you get x is less than negative 7, or x is less than 1. Sorry, greater than 1. Now, this is a graph of what x plus 3 can be. This is a graph of what x can be. Negative 7, 1, and 0 is like here. And I have greater, there's an open circle there. Maybe I should use a different color. The solution's in green here. Greater than 1 or less than negative 7. Okay, so that means that anything in the green region for x, when I put it in to this original equation, should work to solve this equation, or to satisfy this inequality, I should say. So up here, this is a x plus 3 graph, and this is a x graph. And notice that they're just shifted to versions of each other. Okay, now what if we try the absolute value of x plus 3 is less than 4? Okay, so I go back to my concept of the absolute value. Here's 0. Here's 4 units to the right. Here's 4 units to the left. And I've got to get this x plus 3 quantity having an absolute value less than 4. So therefore, it's the distance from 0 to x plus 3 has to be less than 4. That means that I must occupy, x plus 3 must fall within this part of the number line. And how do I describe that number line, or that portion of the number line? I would say that x plus 3 has to be greater than negative 4. X plus 3 has to be less than 4. And the magic word between these two, because I need both of these things satisfied at the same time, is and. I can't just have numbers greater than -4 because that would include all the numbers way out to infinity this way. And I can't have just numbers x plus 3 less than 4 because that would be all these numbers to -infinity over here. I need the intersection or the overlap of these two restrictions. And if you have an intersection or an overlap, you need an and. Whereas up here, we were saying that either this constraint or this constraint would satisfy the equation. Now we need both constraints to satisfy the inequality, and so we have to use the word and. Again, I solve these inequalities separately. X is greater than -7, and x is less than 1. So again, this is, I'll draw another graph here for what x can be. Here's -7, here's 1, here's 0, and now that we've shifted over, I'll mark the solution in green. We're going to be any number in between -7 and 1, and these are open circles at the end because we're simply less than. And so now we've got a solution for x, whereas this one up here was an x plus 3 graph. Okay. I hope that's clear. Okay, one question you might be having is about these open circles. The open circles indicate that all of the points as close as you want to 1 or as close as you want to -7 are going to be included in the solution set. And except the numbers 1 and -7, because if you say put 1 in there and we try it out, we get the absolute value of 1 plus 3, which is equal to 4. 4 is actually not less than 4. So I cannot include 1 in my solution, but as soon as I pick a number just less than 1, just try like 0.9, 0.9 plus 3, 3.9, the absolute value of 3.9 is 3.9, and 3.9 is indeed less than 4. So I can include 0.9, 0.99, 0.99999, as many 0.9s as you want to get me closer to 1 I can include, but as soon as I pick 1 that I cannot, then the inequality will not be satisfied. When to use a closed circle? Well, if we did the absolute value of x plus 3 is less than or equal to 4, then I could include 1 in my solution set, and I would just simply, it would be a very similar graph, -7, 1, and 0, and I would put a closed circle there and a closed circle there, and if I were to do it in green, sorry, I would do, and I would connect them, showing that indicate that all the numbers between -7 and 1, including -7 and 1, satisfied the inequality.
And lastly, I just don't want us to get too far from the fundamental
understanding of the absolute value. So even if you were doing something that was complicated, like the absolute value of ln x is greater than 2, you don't even need to know what the ln function is or what a logarithm is. You can still do the absolute value part of this problem by recognizing that the unknown quantity, ln x, has to have an absolute value greater than 2. So therefore, the unknown quantity ln x must itself be greater than 2, or the unknown quantity ln x has to be less than -2. And if you continue to solve this, you don't have to. That is the work of the absolute value. The rest is understanding what a logarithm is. But for the sake of finishing the problem, I will. This is base e, so that means x has to be greater than e squared. I don't need to worry about the sign direction there because the ln is monotonic. So as x gets bigger, the ln x gets bigger. So I don't need to worry about switching the sign. And then likewise here, x has to be less than e to the -2 in order for the absolute value of ln x to be greater than 2. You could graph the solution. And I guess I want to reiterate what a graph is. I mean, the graph is basically a picture of what solutions make the statement true. And I'm going to put a dot wherever there's a number that makes the statement true. So you should consider all of these. This green wiggly line is just a collection of dots that make the equation true. The open circle is included as a dot, the closed circle is. So if I mark e squared, maybe here, and I mark e to the negative 2 here, it's important to note that where's 0? Well, 0 is over here. E to some exponent is always positive. I'm not sure about the scale, but as long as you put both of these numbers to the right of 0, I'm okay with that. And we're saying greater than, without including, e squared out that way, and less than, not including e to the negative 2. So out that way. Okay, so the point is that when you're faced with an absolute value, don't let it get intimidating. Just look at that and say, okay, I'm supposed to evaluate the distance that something is, an unknown quantity perhaps, from the origin. If you're dealing in one dimension, like we were ever since the beginning of the video, you're going to be working with a numbered line and trying to understand distance from 0 on a numbered line. If you're working in 2 dimensions, which not a lot of people do until college, or even some physics, I guess, if you're working with vectors, then you have to work with the Pythagorean theorem and try to understand the magnitude of a distance from of a point from 0. But I think there'll probably be a different video for that one. For now, just try to understand what the absolute value part is saying, and you should be good. All right, good luck.